In the previous video, we learned how to take the derivative of a natural log function. And now we're going to generalize that result to logs with any base you want, and we're just going to call the base b. And I'm going to offer two different proofs of the rule here. These proofs are both instructive for different reasons. You can consider the first proof to be more fundamental, and we're going to approach the problem using implicit differentiation. And then in our second proof, we're going to use the change of base formula for logarithms, and we get the same answer with way less work. So to start our proof, we let y equal log base b of x. And remember from the definition of logarithms, this is totally equivalent to an exponential equation. We can just turn it around to say b to the y equals x. And now what we're going to do is take an x derivative of both sides. So over there on the left, I have b to the y. It's a function of y, but y is also a function of x. And when we take the x derivative over there, we're going to have to use the chain rule. It's going to produce a factor of dy dx, and that's what we're looking for. And this is the basic idea behind implicit differentiation. So we take the x derivative on both sides. Again, on the left-hand side, you have to view that as a function composition. It's b to the y, but y is a function of x. And on the right-hand side, of course, the derivative of x with respect to x, that's just 1. So remember, when we differentiate an exponential function with a non-standard base, it throws out a factor of natural log of the base. So when I differentiate b to the y with respect to y, I get natural log of b times b to the y. Then the chain rule says we have to tack on a factor of the derivative of y with respect to x. So that's the dy dx that we're hoping to isolate. So we're just going to divide now by natural log of b times b to the y. So we've isolated dy dx written as a function of y, but we want to turn this back into a function of x. So I can replace the y in this exponent with its original definition over here as log base b of x. So we get that replacement done, but then we remember that b to the x and log base b of x are inverse functions of each other. And that means taking b to the log base b of x is just going to reduce to x. So there's our final answer for the derivative of log base b of x. It looks a lot like the derivative of the natural log function. Remember that was 1 over x? But there's a slight side effect to having a non-standard base. We have to put a factor of natural log of b into the denominator. So let's take a look at our alternative proof here. We let y equal log base b of x, but then we remember the change of base formula. So that allows you to rewrite any logarithm in terms of whatever base you want. So I'm going to rephrase this in terms of natural logarithms, in other words, logs of base e. And the way that works is we'll have the natural log of this argument x divided by the natural log of this base b. So y has been rewritten as natural log x divided by natural log b, and now we can just use our old formula for the derivative of natural log x. That natural log b is just a constant there, so it doesn't affect the derivative. So we take the derivative and we just get a 1 over x from differentiating the natural log x, and we arrive at the same answer. The derivative of log base b of x is 1 over natural log b times x. So now that we know how to differentiate logs with non-standard bases, we'll wrap it up with a few simple examples. In our first example, we have the derivative of log base 2 of x, and this is just a direct application of our new formula. That's going to be 1 over natural log of 2 multiplied by x, and we're done. Our next example incorporates the chain rule. So I have log base 3 of this function 1 minus x squared. So we're going to start by taking the derivative with respect to 1 minus x squared, just treating that as a single variable for the moment. So we apply our formula. That's going to be 1 over natural log 3 times that argument of the log function, so 1 minus x squared. So that's what it means to differentiate with respect to 1 minus x squared. But then the chain rule says we have to tack on the derivative of 1 minus x squared, and that's negative 2x. So cleaning things up a little, we'll write that as negative 2x over natural log 3 times 1 minus x squared. Our next example is a little reminder that if I just see log, it's implied that I'm talking about a base of 10. So I have the derivative of log base 10 of sine x. And again, we have to use the chain rule on this, and we start by differentiating with respect to sine x. So we apply our new formula, and we get 1 over natural log 10 times the sine of x, so just 1 over the argument of the log function there. And then the chain rule says we have to multiply by the derivative of sine x. Well, that's just a cosine x. And now when we're cleaning up our answer, we realize there's a nice name for cosine divided by sine. That's just the cotangent. So we could write this final answer as 1 over natural log 10 cotangent of x, and we're done with that one. Now example 4 is just a trick question. If you get too much in the habit of applying our new derivative formula, you could accidentally miss that what we're looking at here is just a constant. So I'm asking for the x derivative of log base 5 of 2. Well, log base 5 of 2 is just some number. And if I take the derivative of a constant, I always get 0. In the next video, we're learning a new technique called logarithmic differentiation. And this is really handy for functions that have problematic exponents. For example, x to the x is the classic example that requires logarithmic differentiation. I'll post a link to that video at the upper left of the end screen, and I'll see you there.